Okay, so today's lesson is the second half of the short lesson that I gave you last time, where I introduced you to the idea of flux by way of explaining electromagnetic induction. So just to remind you where we got up to, we had met this idea of flux linkage, which is the total amount of flux as given by the flux density multiplied by the area, BA, that passes through a coil of wire. So if the coil of wire isn't quite perpendicular to the flux, we need to multiply by a cos term to resolve the flux in the direction of the area, and the formula is on the screen in front of you. So n phi or NBA cos theta are the expressions that we've got for the flux linkage. And then I left you at the end of the lesson with an expression of what's known as Faraday's law, and that's where we're going to pick this up today. So Faraday stated that the change in flux linkage is responsible for the induction of the EMF between the ends of the wire. And he actually went further than that to give a mathematical version of it to say that actually they're directly proportional. We're just going to pick up that proportionality now. We're just going to note that the right-hand side of that formula is dimensionally the same as the left-hand side. So we've got n times cos theta, which are both dimensionless, and then we've got BA over T, which gives us the Teslas from the magnetic flux density. We've got the meter squared for the area, and we've got seconds or per seconds for the divide by time. We then note that the Tesla, remember, is 1 Newton per amp meter from the definition in the formula F equals BIL. And when you work the algebra with all of those letters, it comes out as a Newton meter per coulomb, and a Newton meter is a joule. So we've got joules per coulomb, which is the volt, which is the unit of EMF. So ordinarily we use constant of proportionality to change from one set of units to another. But in this particular case, the left and right hand sides of the equation are already the same as each other, and therefore we don't need a constant of proportionality to exchange the units for us. So in actual fact, because of the definition of the Tesla that we settled on from F equals BIL, we can just write the constant of proportionality as 1, and this just becomes an equal sign. Except it turns out that 1 isn't the best choice. So we're going to meet Lenz now, and Lenz's law is a modification of Faraday's law. And what Lenz said was actually we should be using a minus sign rather than a plus sign for our constant. To be honest, whether a PD is positive or negative really depends on whether you've connected the voltmeter one way or the other way. And so in a sense, this is a symbolic minus sign because it only makes sense if you accompany it with a kind of agreement over which way round you're going to connect the voltmeter to the coil. However, it's there really to remind us of a deeper scientific argument that Lenz put forward, which he said basically that in electromagnetic induction in which we produce electricity, we must always remember that energy has to be conserved. So why might it not be? Well, let's have a little look. So here is a coil with a magnet a long way from it. And what we're going to do is move the magnet near to the coil. And when it gets near to the coil, it has linked to the coil. So we went from a time in which there was 0 flux linkage to a moment later where there was some flux linkage. And during that change, as the flux linked with the coil would have had an EMF induced across the ends of it. So as in the diagram there, one of those ends of wire would have become positive and the other end would have become negative. The question is, which way which one's the positive, which one's the negative? So in order to do that, Lenz gives us a reminder that in order for the electrons to find their way to one end of the coil, they have to flow around the coil. And as soon as an electron flows in a wire, the wire starts generating itself a magnetic field, as we've seen. And when the magnetic field is generated in a solenoidal coil, the solenoidal coil will develop a magnetic field that looks a lot like a bar magnet. And so one end of this coil is going to become a North Pole and the other end is going to become a South Pole. So which way round is plus and minus is the same question as which way round is north and south. So imagine that it's this way round, says Lenz. What if the electrons all move in the direction shown so that the end of the coil on the right-hand side collects electrons and becomes negative, and the end of the coil on the other side loses its electrons and becomes positive? In which case, the electrons will be moving in such a way that the coil will become a south pole at the end shown. And if this occurs, then the South Pole is going to attract the magnet in. Now, that's going to have the effect of accelerating the magnet and giving to it kinetic energy for free. All we need to do is nudge the bar magnet just a millimeter or so, just so it moves ever so slightly, just to change the amount of flux linked just a little bit. And as soon as that happens, the coil will become a very weak south pole. It'll attract the magnet in a little bit more. The magnet will move further. There'll be more linked flux. There'll be more current. There'll be more south pole. And the whole thing is going to run away with itself until we have an ever increasing acceleration on the North Pole. And we're going to end up with obtaining what could be a very large amount of kinetic energy for free. And Lenz says this is ridiculous. He says it must be the case that the other end of the coil becomes the North Pole so that we don't get this energy for free. In fact, quite the reverse. What is then required is that we must push the magnet into the coil because north repels north. And in doing so, as we push the North Pole into the north end of the coil tries to push the magnet back out, and we end up doing work on the magnet to overcome this repulsion. And so we actually end up transferring energy to the system. And effectively what this energy ends up doing is pushing the electrons all the way to the other end of the wire. And this means that we have been responsible with our work done for what we have come to know as the electrical potential energy of the electrons in their location of raised energy. So this force that's doing the pushing is actually the source of the electric energy that we will then tap into when we then connect our electrons to a bulb and light comes out. That light originally came from the work done by the original force. And that force is usually provided by a turbine. So we make something spin and it causes the coil to rotate near to a magnet. And we need that turbine to do that, not because of any frictional forces that are taking place in the bearings of the turbine, but actually because of the magnetic force that the coil is trying to undo the change that's causing it. So whenever you try to push a magnet into a coil, the magnet always tries to get pushed out of the coil by the coil. Historically, the force that creates the motion of the electrons was always referred to as the electromotive force. And this is the original meaning of the letters EMF. It's historically confused because obviously the F stands for force, and we now know that it's not a force. The EMF, it's joules per coulomb. It's the energy of a unit charge, or the energy gain of a unit charge as a result of the force. So a slightly confused term, which is why we always abbreviate it these days to EMF rather than to refer to it by its extended name, because the extended name is confusing and ultimately wrong. Okay, now that we've met Faraday's law and Lenz's law, let's have a look at them in action. So you will remember pictures like this from GCSE, where we've got a coil of wire spinning between the jaws of a magnet, and there's a split ring commutator that will be responsible for taking away the current for us. So this is all familiar to you, the basic setup of a very simple generator. Modern day generators are more complicated than this, but this is the basic principle. And there is Faraday's law with Lenz's correction with it. And what we need to appreciate when we look at this diagram is that the number of times that the wire is wrapped around the coil is not being changed. The magnetic field strength is not being changed because that's a permanent magnet. The area of the coil is not being changed. And so we can pull the N and the B and the A out of that formula. And so all we really have is the change in cos theta as the coil rotates relative to the field, divided by the time taken. So we can see that we are going to get the most potential difference generated if we have a very large number of turns of wire on the coil, although that's up to a limit because obviously copper is heavy, and the more you put on, the harder it will be for the bearings to support the weight of the coil and for the turbine to get it spinning in the first place. If we use a stronger magnet in this particular picture, that's a permanent magnet, and permanent magnets do have a limit to how strong we can make their magnetic field strength. However, in modern generators, we might choose to use an electromagnet, in which case we're only limited by the current that we can put in the wire. And if we cool the wire down to take away the heat, that could be sizable indeed. The area of the coil, so generators tend to be reasonably large, kind of room-sized, but we can't go very much bigger than that because, again, from an engineering point of view, they just become unwieldy to build and maintain and to function. And then we've got delta cos theta over delta t, which is basically the rate at which it's rotating. So the faster that the coil rotates, the bigger the effect will be. However, it's easier to see that with a little bit of maths on the next slide. So if you just take a look at the circular pictures running across the top of the screen, that's kind of an axis on view of the coil. So imagine you're standing at one end of the generator, and the first circular picture is where the coil is in a vertical orientation. So the magnetic field is running horizontally across this picture, which means that the bit of the coil that we're wondering about is the bit at the top and the bit at the bottom, because those are the bits that are going to rotate and cut through the magnetic field lines, and they're also the bits that are on the edges of the coil. So they're kind of executing a circular motion around the axis, which is what the next little bit's coming in. We can see that that angle theta is going to be going round in a circular motion at a constant rate, which we could refer to by the angular frequency omega, as we've met before. And so we've got the angle at any particular moment in time is equal to omega t. So in our formula where we had that the amount of linked flux was BA cos theta, we can now replace the theta with a time varying version of itself, omega t. And so in the formula, we can now replace the cos theta with the cos omega t. And you remember that delta divided by delta t is a rate of change, which is what we differentiate things for. So we just need to take the time derivative of that. And the time derivative of cos omega t is omega sine, but with a minus sign as well. Cos becomes minus sine. And we've already got a minus sign at the front of the equation from Lenz. So the minus and the minus become a plus. And overall, we end up with a positive sine curve. And it's got the omega thrown out front from the differentiation. And now it's explicit that the frequency of rotation will alter the amplitude of the EMF. So there are our four factors, omega, N, B, and A. And then you can see that a minus cos arrangement, a cos arrangement is going to correspond to a sine arrangement for the EMF. So if we were to draw a graph of the flux linkage, as in the graph at the top, so it's going to be maximum when the coil is vertical compared to a horizontal field, and it's going to be 0 when the coil is parallel to the field. So that's what we've got going on at the top graph. That's a graph of flux linkage as time varies across one time period, and that's a cos curve. And below it, we've got a sine curve to go with it. And you can see that when the flux linkage is maximum or minimum. There's not going to be very much rate of change because the coil is practically, it's vertical, and as it moves slightly vertically, it doesn't really change the area presented to the field. So the rate of change is minimum when the flux is maximum. But then when we go horizontal, a small change here makes a huge difference to how much area is presented to the field. And so we get a maximum EMF at the point of maximum flux change, which is when the coil is just passing through the horizontal point.